Hi, hi everyone, welcome to today's session. My name is Sri Krishna. I'm your learner success manager for the day. Before we go ahead with the session, please let me know if my voice is loud and clear.
Yes, Shri Krishna, you are loud and clear. Hello, everyone. I hope I'm
Yeah,
audible to
we can
everyone.
also hear you clearly. Now I will make you the presenter so we can get started with the session. Happy learning, everyone.
Hello, everyone. Good morning, good evening, good afternoon. So let's wait for a couple of minutes so that everyone can join in, and then we'll start with the session. Hello everyone. Hope everyone is doing well. I hope I'm audible to everyone. Okay. Good afternoon. Okay, just a recap, verbal recap of what we did yesterday, and then we'll continue from there itself. So in yesterday's class, we started talking about, and let me share the screen because I have that snap. I've already uploaded it on the LMS portal for all of you. But yes, so this is what we did yesterday. So we started with talk after completing C1, we started talking about probability and what probability is, how it to calculate it. Post that, we also started looking into the applications of probability, that how probability is used across various domains. And then is when we started talking about probability distributions. So what are probability distributions? What is the experiment? And then how they are divided into two: discrete probability distribution and continuous probability distribution. And I just named few of those. Then post that, we started talking about discrete probability distributions, and we started with the most simplest one, that is a Bernoulli probability distribution, talking about that only two possible outcomes can happen for a Bernoulli probability distribution and only one trial is allowed. That is what we looked at, in fact. Post this, then we talked about what is a success and what is a failure. That is what we looked into. And then we took certain example. For example, tossing a coin. If you consider a head as a success, so probability will be what? You are rolling a dice and getting a number less than or equal to 4, and in that case you call that as a success. So you calculate the probability of success, so 1 by 6 plus 1 by 6 plus 1 by 6 plus 1 by 6. So we looked into this, in fact, if you recall it. uh, we looked into all these things. Okay. Post this, then we started talking about the binomial probability distribution. What is the binomial probability distribution? And what are various requirements for it? For example, the requirement is it is based on multiple Bernoulli trials, that you have more than one trial, and but there has to be only two possible outcomes. Probability of success remains constant. Trials are independent, but they are limited. Okay. So then we took an example that, okay, you're tossing a coin three times. So what is the probability of getting three head? But like you can see what is the probability for all the outcomes. So if you recall what is probability distribution? Probability distribution tells you that what are or how is the probability distributed across all the possible outcomes. Okay, probability distribution is simply a formula, or you manually calculate it and place it in a table that tells you how probability is distributed across all the possible outcomes. That is what is probability distribution. And we took a look at this example that, okay, you're tossing a coin three times. So what are all the possible outcomes that can happen? So we did this manually, that had like all these possibility combinations, and we calculated the probability for each of them. Okay, what if zero head, one head, two head, three or three heads, and same goes for tail as well. In fact, so we calculated all this probability, in fact, and that is what we did. So you can see that, okay, this is how your probability is distributed across all outcomes, across all the outcomes. So this is hence what you can say in simple form is probability distribution. Okay. So we understood the concept of probability distribution. That what if we know that these are all the outcomes that can happen, and these are all the probabilities that can happen. So that is what we looked at, and then I put in a question that, okay, what if you're tossing a coin 300 times, and this is where we ended our class, and we'll be talking from this point itself ahead. Okay, but yes, anyone having any questions so far, please put in. So any questions, anyone so far? So let's continue from here only. So just to mention what we have done, we have looked into that what are various probability distributions and what is Bernoulli, binomial, and we calculated it for example that okay, for all the possible outcomes we have the probability, but now comes the open question. What if we toss the coin 300 times? Again, that is where we will come to a question that we'll have to answer now. Do we manually do it? What do we do in this case? Okay. So let me move back to the blackboard and let's discuss this in detail. So I hope my screen is visible to everyone. Okay. And also, please give me a second, everyone. Okay. So our question was what we did. Just to provide a recap. So for toss a coin 3 times, and we calculated the probability for all outcomes manually. Okay. When I say manually, we wrote all the possible outcomes down by hand. When we did this particular part. Now the question that we had is now the question that we had is that what if the toss is done 300 times. Now you can agree with me that if you try to write all the outcomes, very difficult to write all outcomes, correct? Or you can say very difficult to calculate manually. So what if I say to you that okay, what if I say to you that we have a formula for it? So what we initially did, we took a simple example, did all the calculation manually, and also figured out that okay, this is a probability for all the possible outcomes. Now see, the questions can be of any variety. There could be uh, uh, 300 tosses, or there could be questions around pulling a card from deck, or questions around rolling a dice, or questions around picking a ball from the bag, or it could be any kind of question. So it becomes very, very difficult for us to write all the possible outcomes, correct? So what if I say that we can use a formula? We can use a general formula for all the cases where binomial distribution is followed. Means that what if I say that instead of doing this whole manual calculations, and as I mentioned, the questions can be of infinite variety, okay, and it's not possible to simply write all these things down. So what if I say that if any experiment belongs to binomial distribution, what if I tell you that there is a formula that we can use and it will directly give you the probabilities? It will directly give you the probabilities. So isn't it good? So some of the researchers, or you can say some of the scientists have done this for you. So we have a formula. We have a generalized formula. Now for discrete probability distributions, now what is the name of it? We call it probability mass functions. Probability mass function, PMF. And just to specifically mention that this is for discrete probability distributions only. Means this probability mass function is for discrete probability distributions. Okay, you might ask now, don't we have formulas for continuous probability distributions? We do have it, but the name is probability density function, PDF. For discrete probability distributions, the name is only for discrete probability distributions. We call it probability mass function. Okay, are you getting a sense of why we need a generalized formula which we can simply use and get the outputs? Because it is not possible to do it manually for all the variety of questions. So why not if we have simply a generalized formula which we can use as a plug and play, and that can simply give us the probability of any outcome that we want. The only requirement is that the data should follow a binomial distribution, or the experiment should follow a binomial distribution. Now your question would be, how do we know it follows the binomial distribution? Based on the requirements which we have talked about. That there has to be a limited number of multiple trials, correct? If you recall, each trial can only have two possible outcomes. The probability remains same at every trial. So these are the three requirements. If these three requirements are met, you can go ahead and directly use the binomial probability distribution formula. The probability mass function of binomial distribution, you can directly use the formula. Now, what is the formula for that we are talking about? So the PMF for binomial distribution NCX, PX, QN minus X. Okay. Now, just to write these things down, what these things essentially mean. So, Does it make sense? So what it is that the PMF for binomial distribution is NCX, PX, Q, and minus X. Okay, where what is X? X is the number of trials which you desire success. For example, in our case, in our earlier example, we said that okay, if you are tossing a coin three times, getting a head is success for us. Okay, so what is the success of getting three heads then? Okay, what is the probability of getting success in every trial? That is what we are saying. What is the probability of getting success in every trial? Okay, and n is the total number of trials. P is the probability of success at each trial, or you can say probability of success at each trial. I've simply mentioned so that it's clear, because sometimes you might hear people saying that okay, getting three head six success for me, but success is always at the individual trial. Okay, getting a head, getting a tail, getting a king, getting a black ball. This at a single trial is considered as success. Now, how many times you achieve success in the number of trials? That is a different thing, but still, I just mentioned it that way. And Q is simply the probability of failure. Okay, and then I also elaborated what is NCX. It's a combination part. You might have studied this during your colleges or schools, which is simply n factorial divided by x factorial into n minus x factorial. Okay, this exclamation mark is what we call as factorial, just to mention. This is what we call as factorial. Now, what is this factorial? For example, if someone says 3 factorial, it simply means 3 into 2 into 1, like all the way till 1. You multiply all those numbers. 5 factorial is equal to 5 into 4 into 3 into 2 into 1. Just so that anyone who is unaware about this concept knows about what is factorial. So far, clear to everyone? Any questions, anyone? Now let's write a question and then calculate. For example, let's try to solve the same question. In fact, the question is, what is the probability of getting success, which is equal to head for a toss? Same example I'm doing example. Same example I'm using in fact. What is the probability of getting success? That is equal to head for a toss of coin. Okay. Or what is the probability of getting success at every at let's say it this way. At every toss of a coin, if the coin is tossed three times. Now if I simply try to plug in the values, so what is our PMF? We just looked at it. It is NCX, PX, Q, and minus X, correct? Just to show you above, this is what it is, correct? If you calculate this, so what is N? N is the number of trials. So how many trials in our case? Three, correct? Three times you're tossing the coin. Okay, what is X? Number of trials in which success is deserved. Okay, number of trials in which success is deserved or desired basically. So how many times we want the success to happen? Three times. Please give me a second, everyone. Let me try to do something around this flickering of scroll bar. Please give me a few seconds. So it was NCX. Just give me a second. Let me stop the share and do it again. Please give me a few seconds, everyone. So I hope my screen is visible to everyone. Okay. So we're calculating for our question. So it is 3C3. And what is the probability of uh, this part? Sorry, this part. Probability of getting a success is 1 by 2, correct? So 1 divided by 2. How many times you want the success? 3 times. Correct? Multiply. What is the probability of failure? Because this is Q, correct? Q is refers to failure. So getting a tail is also 1 by 2. Or simply 1 minus 1 by 2. That is what you can say. How many times you want a failure? 0 times. So 3 minus 3 essentially. Okay. So if you calculate this, it will come out to be, because this simply goes to 1. Okay. And this also comes out to be simple 1. And hence you are left with 1 by 8. Hence 0.125. And that was the probability, if you remember, of getting 3 heads in a row. Do you agree? Questions, anyone? Which particular part? Okay. So what was the case? Initially, we took an example where we were tossing a coin three times. And what we did, we calculated the whole, all the outcomes, like we figured out all the outcomes manually. And then we calculated the probability for all the outcomes, correct? And it was just three tosses and the number of outcomes were eight. Now the question is, what if there are 300 tosses? Is it easy for a human to simply write down all the possible outcomes and do the calculation? The answer is no. So what to do? That is where we say that, okay, what if we have a generalized formula that can be simply used if the experiment follows the binomial distribution. Okay, now your might question might be that, okay, what is a binomial distribution? Basically, which has multiple trials. Every trial has equal like this constant probability. I'll not say equal probability, constant probability at every trial. Like the success and like it has two out. Okay, just to repeat from starting. So what if there are 300 tosses? Not possible to do manually. So what if I say that we have a generalized formula for an experiment if it follows binomial distribution? What if then we can simply use a formula. That makes your life easier so that we do not have to write down all the outcomes by ourselves and do the whole calculation. Now I said that you can use this formula only if the experiment is following binomial distribution. Now what is the meaning if it is following binomial distribution? How do we know that? If there are multiple trials, there are 3 to 4 requirements for binomial distribution. First, there has to be multiple trials. Second, every trial can only have two possible outcomes, success or failure. As a user, you decide what is success, what is a failure. Third, the probability of success and failure remains constant at every trial. Okay. Fourth, all the trials are independent of each other. So these are the 4 requirements. If an experiment is matching all these 4 requirements, you say that, okay, it's a binomial or binomial distribution experiment. So you can directly use the binomial probability distribution formula that we'll be talking about now. So as I mentioned, multiple tosses, what to do? You can simply use the formula or multiple. There could be many experiments. We'll look into one more example, in fact. Okay. So we have a generalized formula. We call this formula as probability mass function. Okay. What is the formula? So this is a formula, and it again has been derived. We are not going to look into the derivation, how this formula came into existence. There have been whole complete derivation. You can look into a web how this formula has come into shape and how it has been derived. But that is not what we are going to do. But yes, this is the probability mass function for discrete for binomial probability distribution. What is a function? NCX, PX, Q, N minus X. So this is the formula. Okay, this is the formula. Now, if you talk about what is this NCX, NCX is simply the combination part. What is P? P is the probability of success. X number of trials in which we want the success. N number of trials. Q probability of failure. And again, all the other variables are same. Then what I did, I simply also explained what is NCX. You can write NCX as n factorial divided by x factorial into n minus x factorial. So then I also told you that, okay, what is a factorial essentially? Like if someone says to you 3 factorial, so it is simply 3 multiplied 2 multiplied 1, like this particular part. So for those who are not aware about it, that is why I've written this over here. 5 factorial example, 5 into 4 into 3 into 2 into 1, all the way till 1. Now we have defined a formula that, okay, this is a formula that we have. We have talked about this. Okay, this is the formula that we have. Now, can we use it for our own example that we were having earlier? The answer is yes, we can do that. How? So let's say our question, writing the question down again. The question was, what is the probability of getting success that is equal to head, basically in our case? It's again, as I mentioned, is user defined. At every toss of a coin, if the coin is tossed 3 times, means essentially what you're saying, what is the probability of getting 3 heads in getting a head in every toss of a coin? Okay, that is what the intent is. And what I've done, I've simply written down the PMF for the binomial distribution. Why? Because is my question or is my experiment following the binomial distribution? The answer is yes. How? Multiple trials. And if I'm tossing a coin, I know the probability is 1/2 for head, 1/2 for tail, and it does not change. It doesn't matter if I toss my coin 2,000 times or 2 million times. Okay, Uh, all the tosses are independent of each other completely. There has been no mention that they are dependent upon each other. Okay, so for me, I know that, okay, this follows the binomial distribution. Now it follows the binomial distribution, so I'm using the binomial distribution PMF for calculating the answer. So what I did, I simply placed in the value. What is n? N is simply the number of times the toss has to be done. 3. X, how many times I want head to come up? I'm saying at every toss of coin. Okay. What is P? P is probability of getting ahead. That is 1 by 2. How many times I want it? 3 times. Okay. Then Q, what is the probability of getting a failure? 1 by 2. How many times, or you can say what is the power? So 3 minus 3 simply 0. Now if I simply expand this formula, if that is the question that how you got this value, let me do that. So it will be 3 factorial divided by 3 factorial into 3 minus 3 factorial, correct? And 1 by 8 into 1 by 2 power 0, correct? Now, can I cancel 3 factorial with 3 factorial? The answer is yes. So 1 divided by it becomes 0 factorial. What is 0 factorial? 0 factorial is 1 only. Okay. So this multiply 1 by 8. What is anything power to 0? What is the value? If any number having power 0, what is the outcome? The answer is 1, correct? Hence 1 by 8. Okay, hence that is what I've written above as well. Carry or update 1 byte, so 0.125. If I remember the value correctly, this was the value. Does it make sense now? If this is the calculation you are looking into. So we did not have to write all the outcomes manually, did we? So we did not write any of the outcomes manually, calculated it manually, nothing we did. We simply used this particular formula and did the whole calculation, and we got the outcome. Okay, that is what we did. Any questions, anyone? Is it clear to everyone? Okay, so now let's take one more question and try to see. So I'll take this question. You might be able to relate to it, in fact, much more well. The question is, what is the probability of a student getting 8 answers correct out of 10 multiple choice questions where every question has 4 options? Is the question clear to first of all everyone or not? For example, I hope every one of you would know what is a multiple choice question. For example, there are questions that are given, and then please give me a second, everyone. Okay. So it says that okay, what is the probability of, and I hope everyone knows what is an MCQ question. Like you have a question, and there are 4 possible answers and you have to select one, correct? Another three are wrong. I hope everyone knows about how multiple choice question. Now, this could be a very valid case. You might be giving an exam and you want to simply calculate the probability of you getting eight questions correct randomly. When I say randomly, by simply guessing that, okay, let me say A, B, C, now let me say C, now let me say D, with what you might have done in fact sometime, or it could be that you might have not done it. But what is the probability of such a thing happening? Now, first of all, is it following binomial distribution? What do you think? The answer is yes, because we have 10 questions. Every question, in every question, there is only one choice that is correct? So the probability of success and failure does not change at all with respect to any question, correct? So what is the probability of success? 1 by 4. Probability of failure, 3 by 4, correct? So does it change with respect to any question? The answer is no. Is a question dependent upon each other? The answer is no, they're completely independent. So can I use binomial probability distribution? The answer is yes. So what we'll do is simply use the PMF formula. So which was what? NCX, PX, Q, and minus X. Okay, so let's calculate first of all probability of getting a success. So what is the probability of getting a success? 1 by 4, correct? Probability of getting a failure, 3 by 4, correct? What is X value? X is 8 because we want 8 questions correct. What is the total number of questions? 10. So far clear to everyone? So if I plug in the values, it's 10C 8 1 by 4 power 8 Q, sorry, 3 by 4 10 minus 8. Now see, these values are far more big, correct? For you to even calculate these things now manually again is an effort. For you to do these things manually and calculate this whole thing again is an effort. So there is one more easy thing that we can do. So now if I say we can calculate it, okay, we can calculate it. But there is a easy way. But there is a easy way. Okay, what is that easy way? The easy way is to simply look at a table and get the answer. Means someone has already populated a table for all of you. Okay, and you simply can go with your probability values and get an answer. Okay, this is what we call as a binomial probability distribution table. Okay, is it making sense? See, I can do this calculation manually, but what if I say that it is far more easier? The first method was simply writing all the possible outcomes by yourself and then doing the whole calculation by yourself. Then came up a formula which is far more easier. You simply plug in the values, no more need of writing all the things down. And now the third part, when I'm saying you do not need to even write the outcomes. You do not even need to use a formula. You simply need to use a table in which all these values are calculated for you. Doesn't it look much more easy? What do you say? So that is what we'll be doing now. So let me open up a binomial probability distribution table. Okay. And then we'll see how you can simply get the probability for it. So far clear everyone? Where we are, what we are doing? Because this acts like a story. That is the intent of me narrating it in a such a way. It is sequential. So let me stop the share and let me open up a web and go to binomial probability distribution table. And don't worry, I'll show you everything. It's not that you'll be easily able to relate what I'm trying to say. And this table is uniform, but does not change with respect to websites. So is my screen visible to everyone? So I simply searched binomial probability distribution table. Okay, there was a spelling mistake when I typed it, but yes. Do you see this? I simply Googled it, nothing else. Now you can go to any website. So this is the first website, University of West Florida, and there is a PDF file. So this is the table which looks something like this. Now this is a binomial probability distribution table which you can see here itself, in fact. Do you see this value over here? What they have written? It's a binomial probability distribution table. Why we are at this? Because we don't even want to calculate using the formula. We want to make it much more easier. Now, what is the probability for our success? 1 by 4. What is the probability for it then? 0.25, correct? So first, in columns, as you can see, it says this is P, which is the probability of success. So we simply select what? We simply select the column that refers to the probability for our success, which is 0.25. This particular column is what we'll be looking into. So far clear to everyone? Now you can see over here n and x is there. What is n in our case? It is 10. What is x in our case? It is 8. Correct? So let's first of all go for n where it is 10 and x where it is 8. Let's do that. Okay, we are at this place now. Do you see? This is n. So n is 10 over here. X, how many questions you want? Correct? 8. Are you able to see first of all, everyone? Please give a thumbs up if yes, what I'm saying. So this is the row that we need to look into now. So this is the probability, in fact. Okay. So what is the probability of you getting 8 questions correct out of 10 questions when there are 4 multiple choice questions? So it is 0.0004%. I hope you're able to relate to this question because most of you might have gone through these kind of examinations, but yes. So it's never a good idea to simply guess all the questions correct. Whereas if you take the probability of getting a failure as success in like getting a wrong answer as success, so probability of that will be much more higher. Just to talk about it in a different manner, everyone please listen carefully what I'm trying to say so that you do not get confused. See, for our case, what we are saying probability of success is getting a question correct. Do you agree? Getting a question correct. What if I say that getting a question incorrect is success for us? Then in fact this is a column that will be of our use, because what is the probability of success now? It will be 3 by 4. Correct? Getting a question incorrect is what we are calling as a success now, and getting 10 questions incorrect out of 8 questions, the probability is 28%. Do you see? Is it making sense to everyone or not? Please answer. So it's never a good idea to guess in a multiple choice examination. But what if, just if we try to nail it down, what if out of 4 questions, you are only able to bring it down to only 2 questions, like only 2 options that you are saying that, okay, this is not the answer, this is not the answer. For sure, it is between these two. Let's say if you are able to bring it down to 2 based on your calculation or based on your something XYZ thing. Okay, that's a different story. But now the probability of success comes out to be what? 1 by 2, correct? Assuming that for every question you are able to do it. For every question you are able to eliminate 2 and you're able to narrow it down to 2. In that case, the probability comes to 0.5. So that increases your chances a bit, in fact. Okay, it increases your chances to 0.04. Rather than 3 zeros, now you're only having 1 zero. Does it make sense? So this is what is binomial probability distribution. I also took an example that you can relate. That is this question answer question that I took as an example. Hope you are able to relate. So is it clear to everyone? Any questions? Please put in. And I simply Googled this binomial probability distribution. I do not have any specific link because it's a generalized table that is present across the web. So any questions, please put in. If no questions, please let me know. We can move ahead then. Please write clear if no questions. Let me do one thing, if that is okay. Let me share the link of this particular table with all of you, and let me share the notes that we have written so far, so that you can just revise the binomial distribution. And then once you are done with it, then we can move ahead and talk about the Poisson distribution. That is another distribution we'll be discussing. I hope that helps if everyone is looking into that part. Not necessary, it depends. See, decimal can go till any level. Away, division can keep on going and going and going. It's not limited to only 4 decimal places. You might have different tables where uh, the calculation is simply at 2 decimal places only. So the probability of failure, if it boils down to two answers, will be, because then essentially you are saying that you are only having two choices, correct, in your question. So probability of success is also 1 by 2. Probability of failure is also 1 by 2. To be. So in that case is when I was referring it to. So I shared the notes as well as the link of the distribution table. So please have a look at it. Do let me know once you are done, so that then we can move ahead and talk about the other probability distribution. Is everyone clear? Please give a thumbs up if yes. Okay, perfect. So revise the notes. Go to the link. Once you have good understanding of uh, this binomial distribution, then we'll move ahead and talk about Poisson distribution, another distribution. So has everyone gone through the notes and the link? Please give a thumbs up if yes. Or you're still going through it? Okay, perfect. So let's move ahead and let's talk about the next probability distribution, that is Poisson probability distribution. Okay, so let me share the blackboard. So I hope my blackboard is visible to everyone. Okay. So now we'll look into the Poisson probability distribution. So just to give you a recap, we are currently talking about probability distributions, and in probability distributions, we are specifically talking about discrete PD. And in discrete PD, we have talked about Bernoulli probability distribution, binomial PD, and now we are talking about the Poisson PD. PD stands for the probability distribution. So the third one is Poisson probability distribution. Okay. So let's talk about this. So let me first of all write the definition, then we'll talk about this in detail. Okay, so what is Poisson distribution? So Poisson distribution is used for a case when an event is happening over a specific period of time. I'll give in certain examples, don't worry. The only requirement is that we have that the event occurs independently and we have an average rate, in fact, that what is the average rate of a thing particularly happening. Let me move into the example and then we'll be able to understand this in detail. For example, number of customers visiting a website in a day, number of customers coming in a restaurant in a day. Okay, or it could be, for example, third one. Let's look into this. So what was this saying? So it is used when an event is happening over a specific or fixed period of time. Okay, and we have some average rate or average value basically. So it is, for example, number of visitors visiting a day, visiting a website in a day. So for example, if I say that okay, there are 100 visitors on a website in a day, in a day. So what is the probability of 20 people coming or visiting the website in a day? Visiting website in a day. So this is kind of the question that you might look into. That was the probability of 20 people coming and visiting the website. Same way that on an average, let's say 1000 people come to a restaurant. So what is the probability that only 10 people come in an hour? Or let's say 2000 people come in an hour. Okay, what is the probability of this? So that is what we tend to do using the Poisson distribution. Okay, so in Poisson distribution, we tend to get the probability distribution of an experiment where the event happens over a specific period of time. Okay, that is what we tend to do. For example, on an average, let's say in 4 hours, I get 80 questions. So what is the probability that I might get 150 questions in 4 hours of the class? Okay, just assuming. So this is how it would be labeled to Poisson probability distributions. Okay. Now it has certain assumptions as well, or requirements. The first one is that event occurs independently. That is occurrence of one does not affect other. Okay. Second, the average rate lambda is known and is constant. So these two are the requirements, or you can say the assumptions of Poisson distribution. Is the example clear what I'm trying to say? What is Poisson distribution? Okay, when you have a specific period of time, and with respect to the specific period of time, you want to calculate the probability. Okay, what is the probability of this person running the race in, let's say, 10 seconds, when on an average the person runs in 11 seconds? Getting it? So probability and all those things, in fact, getting a calculation of all those things. That is when Poisson probability distribution would be used. Okay, these are the assumptions. Now, does it have a PMF? The answer is yes. Now, what is PMF for this? Just to write it. where n is basically the number of events. Lambda is simply the average event rate. E is simply the Euler's constant, which is 2.718. Okay, the value of E is already defined. It's the Euler's constant. So let's take a question for this and let's try to solve that as well. Let's say the question is, what is the probability of a hotel receiving 8 guests in a day when the average number of guests that arrives in a day are 3. Okay, so how you can calculate the probability? For calculating the probability, we'll use a PMF only. Okay, the PMF of Poisson distribution. First, you need to check, does it follow the Poisson distribution? Yes, because we have the average number of guests in a day, which are 3, and we are saying that okay, what is the probability of getting 8 guests? So specific period over time, a specific time frame, in fact, and we are want to get the probability with respect to that. So if I say what is lambda, what is lambda? If you recall, the constant average rate I have specified over here. So lambda is equal to what? Lambda is equal to 3. What will be n is equal to? And if I show you the formula also so that you can have it in view, n will be 8. So what is the probability of getting 8 customers? If I simply write this formula, it will be 3 power 8, 2.718 power minus 3, because it's minus lambda, divided by 8 factorial. Correct? Not 8, sorry, 3 factorial. Sorry, yes, my bad, it's 8 factorial, correct? Correct. So 8 factorial, correct, my bad. Okay, so this is how it will look, and if you calculate it further, you'll get the probability of 8 guests arriving at a hotel, and on an average, 3 guests only come in a day. Okay, clear to everyone? Now, usually we do not have a table for Poisson distribution. Why? Because see, the values can be till n level, correct? It can occur till n level because it can be any number of average values, any number of uh, things that you would want to calculate probability for, correct? Do you agree? So hence, making a table is not possible. But what if we try to solve this in Python? What if we try to solve this whole formula in Python and see whether we can do it or not? What do you say? Okay, do one thing, everyone. Open up your Python notebooks. Let's see if you can give me what is the value of this. What is the probability for this particular thing using Python? Let's see how many of you can do it. So let me stop the share also. In fact, I'll be sharing the Python notebook myself. In fact, so let's do it. In fact, just give me a second. Anyone able to calculate the probability using Python? So I hope my screen is visible to everyone. Is my screen visible to everyone? So this is the PMF that we have just to show. So this is the PMF formula. Let me also bring in the question snapshot. Okay, so this is the question. Okay, what is the probability of a hotel receiving 8 guests? This is the question. So can you do this calculation in math? Using Python. That is what the intent was. Can you please open your Python notebooks and let's see how many of you can do this. Okay, let me do one thing. Let me help you with this then. So let's make a lambda formula. Okay, and lambda will receive a lamb value and will receive, let's say, before this we also need to import math. So let's say from math, what it should return? It should return basically three things that will do. So one is the lamb. Let's not call it lamb. Let's call it lamb. Lamb power what? N. Okay, so one is this multiply by 2.718 power minus lamb. Okay, so this is the numerator that we have written over here. Now just to write the denominator, simply factorial and simply n. Let's call this function as Poisson probability. So now if I simply say Poisson probability, pass in lambda. What is lambda for us? 3. And what is we want for 8? Just give me a sec. It should be underscore over here. So the probability is, okay, I think we are doing something wrong. Okay, it's power, not multiply. My bad. So the probability of happening such a thing happening is 0.008. Does it make sense, everyone, what we are doing? Okay. Now coming to another question. So this is a question for all of you. Let's see how many of you can do this, and you need to share me the code for this privately. Okay. Now the question is for the for lambda value from 1 to, let's say, 30, and n value from 1 to 50. Make a pandas data frame where lambda values are in column and n values are as index. Okay. How many of you can do this? So this is the question. So for lambda values from 1 till 30, I want the probabilities for different values of n from 1 till 50. So when lambda is 1, what is the probability from 1 till 50 for different values of n? Okay. Same way when lambda is 2, probability from for n being from 1 till 50. How many of you can do it? Lam is it a variable? This one? This is a variable, yes. First of all, do let me know how many of you have understood this code. What is this code doing? Can you tell everyone? What is the selected code doing? Are you able to understand? Yes, it is calculating the probability. Okay, let's do one thing. Let's stop over here, and after the break is when we'll do the question that I was talking about. I'll give you time at that. Let's go for a break as of now. So let me launch the poll first, then we'll go for a break. And after the break, we'll continue and try to solve that problem. That will also assess the capability of all of you in Python. I hope everyone has polled. So ending the poll, sharing the screen with the timer. I hope my screen is visible to everyone. So is my screen visible to everyone? Okay. So let's go for a break. See you after the break, everyone. We will be talking about the Poisson distribution, a question that I gave to you, and we'll try to solve that, and also see the graph for the Poisson distribution as well. In fact, that how for different values of lambda, the Poisson distribution graph changes. So that is what we'll be doing. So let's go for a break and see you after the break, everyone. Thank you. I hope everyone is back. Okay, so let me share the screen and let's talk about that question now. So I hope my screen is visible to everyone. So now the question is for all of you, write a Python function which takes in a range for lambda and n, okay, and returns a pandas data frame. Now what needs to be done? What should be the output? The output should be for every value of lambda present in the range given, get probability for every value of n with respect to the range given for n. Okay, so this is the requirement where lambda values are in columns and n values are as index. And do not and let me do one thing. So this is what you need to do. So how many of you can do this in fact? However, every one of you should be capable enough to do this by now by yourself, because you already have gone through pandas, you have also covered Python, so you should be capable enough to do this. So do one thing, take 5-10 minutes, try to solve this and give me a Python function in which I'll simply pass in the range for lambda and n, and in return I'll get a data frame, okay, where the all the range that I gave for n should be as an index, the range that I gave for the lambda should be in columns, and the values should be representing the probabilities. Okay, is the question clear to everyone? Please give a thumbs up if the question is clear to everyone. Okay, let's see how many of you can do this. No web of it will require modification. That's not correct. I've written the question much more clearly now. But let's see how many of you can do this in fact. So you already know the basic looping and all those things that we have already covered in Python. Let's see how many of you can pull this off. Okay. Just to mention, it can be any range, Sudhir and Toby. So that is what the requirement of the function is, correct? A user, for example, if I'm using this function, I can pass any range of lambda. Could be from 5 to 80, could be from 2 to 6, could be from 5, could be from 10 to 15, could be any number. We still have to write a function in that particular manner. Okay. Bharat, why you are taking the sign values of lambda? I'm not able to understand that. That's completely different than what we should be doing. Incorrect. It's not correct. Protic, you need to write the Poisson PM formula as well. Uh, so how will it take n and lam value? Where is that function? So it will give error. Maybe same goes for you're only taking the n range. You're not taking the lambda range. Where is the lambda range? So that will give a lot of errors, in fact. Not correct. Okay, so let's see how this can be done, and let me try to write the code around it. I'll write it from scratch. So let's see. I hope my screen is visible to everyone. Let me just check. So first of all, if you were facing challenges even in doing this, so you need to practice a lot, honestly. Uh, in case if your rule is will require you to write codes and programs, okay. So you'll have to improve a lot in that case if you were not able to write it. Okay, just to write the code. So let's make the name of the function as Poisson table. Let's say Poisson table. Okay, what it will take the lamb range which I mentioned and the n range. Okay, so let's also import pandas library before it. Okay, now let's simply create a data frame. Okay, let's simply copy our function that we have written over here, Python p. Okay, now what I can simply do is I can simply say for lamb in lamb underscore range. I'm simply making a list of probabilities. Then inside this, as if for n in n underscore range, I'll simply first of all calculate the probability. How? By simply saying Poisson underscore p, like this particular function that I've written over here. And inside this, I'll say lamb and n. Okay. And I'll also append in case if I want to. Let's do this. So yes, let's append this. So probabilities dot append prob, and then I'll simply make the column in the data frame. So I'll simply say df, and let's make this f string lamb underscore, and I'll simply make this over here lamb arobs first of all, and then finally I can also say df dot index is equal to list of n underscore range, in case if it is a range. Okay, if it is a list, it should be already converted to a list, and then simply return df. I hope I have not done any error, syntax error, those mistakes. Let's see how it works. So let's call the Poisson table now, and for lambda range, let's pass in range from 1 till, let's say, 30, and for n, let's pass in range from uh, let's say 1 till 50. Let's see what we get as output. Okay, so we are getting, so let's also do the round off for probability because it's quite a high number, means a lot of precision is there. So let's round it off to 7 decimal places or 5 decimal places. Let's see this. Yes, and yes, now you can see that what we are having is for all the values of lambda, we are having all the values of n, as you can see, all the 50 values. Okay, so it starts why it is having 49 because I passed in 50, so by default it goes till 49. And you can see that I have this. If I reduce this range to, let's say, uh, only till 30, so it will be a bit short now, but yes, so this is how it can be simply done. Now what I also wanted to show you is, and let's say this, the table that we got, table this, and simply table. Now I wanted to show you the graph for Poisson distribution as well. That was the intent of getting this. So this is our table, correct? So I can simply say dot plot. That's it. So can you see how with respect to different values? And let's do one thing, because we are having a lot of lambda values. That's why it looks like this. Let's make it 10. I hope the graph. Can you see how for different, as the lambda value is increasing, how the graph is moving? Like when lambda was simply 1, it was like this simply, correct? But as the lambda value is changing, do you see how it is moving like this? It's moving towards center like this. So what I can conclude that for bigger values of lambda, the graph might look like this. That probabilities being similar, that it might look even symmetric. Okay, what we can do is we can even try to do that itself. We simply need to change the values. So if I say instead of 10, let's call it 16. So we'll get till 15. So yes, do you see this purple one, last one, lambda 15? How good of a graph it is. It's completely symmetric around, in fact. Okay. So clear to everyone? Any questions? Okay. So what we were able to do for all the different values of lambda, now you can get different, like you can get the probabilities for different value of n. And what we can also do is we are able to plot a graph also from it to see how the distribution goes, in fact, how the probability distribution looks like. So any questions, anyone? Any questions? Please put in. This is the PMF, Toby. This itself is the PMF formula written. So we simply calculated all these values with respect to PMF, but now try to understand. It could be that the number of visitors visiting a website could be 40,000. So for all the possible values, you cannot have a table. That is what I was saying. Okay. So that's why you do not have a table for Poisson distribution, because infinite or good number of values combinations can come up. For 30,000 average number of visitors per day, what is the probability of one visitor, two visitor, all the will take till million, 10 million, whatever value you want to put. Okay, so it's not possible to note down all the combinations. So is it clear to everyone? Any questions, please put in. So has everyone understood the code as well? Okay, perfect. So this is what I wanted to show, and this is essentially the graph also I wanted to show, that how the probability distribution for Poisson distribution changes with respect to different lambda values. As the lambda value keeps on increasing, it looks a bit more symmetric and it moves towards the right side. Okay. Now, perfect. So now let's do one thing. Let's move to Blackboard back again, and now we'll start with the continuous distributions. Okay. So stopping the share, and let me share the Blackboard. Is there a way we don't have to write the PMF function? Yes, you can import it from libraries as well. But if you're saying, can we do it without using the PMF function at all? The answer is no. Then how will you get the probability, Rotik? If you are not using any formula or function, how will you get the probability? So is it clear to everyone? Any questions? Any doubts? Okay, so let's move ahead. Now let's talk about normal distribution. Yes, Pratik. You can only get the probability, not the whole table. So we simply wrote a function code for the table. There is a code for the function present in SciPy in these libraries, but not a code for getting the whole table. And honestly, the PMF for Poisson is quite simple and quite easy. You will be really rarely using any of the library because it's very easy to write by yourself. The difficult ones are the continuous probability distribution functions, which have to be integrated with certain limit. Okay, that is where it's challenging. Okay, so far we have seen a discrete probability distributions. Just to give you a recap, we started with what is probability, what is Poisson, what is probability distributions, and then we moved into the discrete probability distributions, talking about Bernoulli, binomial, what is a PMF, then talking about the Poisson distribution as well. And now is when we are moving to the continuous probability distributions. So let me write that now. Okay, so the first one that will be learning is normal probability distribution, also known as Gaussian probability distribution. Now, because it's a continuous probability distribution, so this distribution is for a this distribution is for the continuous theta which I mentioned. Now, this distribution is very evident in nature. So it's very evident in nature. For example, if you collect any data from a population which is continuous in nature, you will be most likely to see the data following a normal probability distribution. Example, if you simply note down the height of people in a city, okay, or let's say weight of people in a city, or IQ of population, and so on, so on. Means, how will it look? How will it look? Let's say, you are having, you noted down the height of people. So this is height of people. And let's say this is simply the counts or occurrences. Now you'll agree with me that when you simply note down the height of people of a particular city, this is how it might look. Okay, so let's say we start with 4.6. So we are starting with 4 to 4 point, or 4.4 to 4.6. However you want to kind of keep it. 4.6, 4.8, or let me make it a bit small. Correct? This is how it might look. Do you agree, everyone? Have a look at the graph and think about it. What do you think, everyone? Am I audible to everyone? Like usually the counts will be highest for the height range of 5.6 to 5.8. Of course, it depends between regions as well. But let's take some common city that you might think of, or city with or usual heights basically. So this is how it might look, correct? So can I say, just think about it in this way now. So can I say if I pick a person randomly, pick a person randomly, the probability of the person falling in this region will be the highest. Can I say that? If you simply pick up a person randomly, the probability of the person falling within these brackets is the highest. What do you say? Correct. Why? Because the occurrences are high. So because this is kind of the most common heights that you can see. So can I say if I simply pick up a person randomly? So mostly the person falls. The probability for this region is the highest. Is highest. Okay, for this region, and for these region, of course, the probability is lowest. If you simply select a person randomly, you might find a person to be 6'8". That is very rare, and same way, person being 4'6", very rare. Highest probabilities for this particular area, or you can say this particular area. Correct? Any questions, anyone so far? What if I simply try to draw a distribution now on top of it? Like I'm trying to make a graph, a distribution graph on top of it. What does it mean? Does it make sense? That what it is trying to say? It's trying to say that this region has the highest probability region. These areas has the lowest probability uh, region. What do you think, everyone? And same would be the case for weight as well. Same would be the case for IQ as well. Correct? Same would be the case of marks attained or percentage attained by the people in a class or somewhere like this. Okay. So this is what we call as normal distribution. Because it is so evident in nature, you record any data with respect to a population, you'll see this kind of thing following up. Okay, this kind of thing you'll see following up. Now, if I try to bring in a graph, just give me a few seconds. Let me try to bring in a graph and show you what really it is in fact. Also, before bringing in the graph, in fact, let's make one more graph on top of this. So what we did, we simply said, okay, this is the count occurrences, this is the height of the people. Now, if I try to make a graph on top of this, and let me insert the line again. So if I simply see height of people over here now, and if I try to make a graph now with probability density on y-axis, this is how it might come up. This is how it might come up. I hope now it's visible. So height of people, and what is this? This is the graph. Now see what we were doing, what we initially did, we simply made a histograms just to mention these are the histograms. Okay, these are the histogram. This is a histogram. Now, what was histogram doing? We simply had the count or occurrences on y-axis and height of people on the x-axis, and we were able to understand and in fact agree that this is how, if you simply try to write down the heights of all the people, this is how it might look. Most of the people following within an average height. Okay, and then what we did that, okay, what if I simply try to make a, a line that is joining the center of all these, you can say, boxes. So how does it look? Can I call this probability distribution? Yes, because it essentially tells me that this region is having the highest probability chances if you simply pick up the person. So within this region, the chances are very high that the height of the person would be from 5'4" to 6 or 6.2 majorly. Okay, but very few people are having this, so hence the probability of this is very, very less. So this was simply a histogram. Now what we did, we simply removed the histograms, and this is essentially what we are left with. Okay, this is what we are left with. Now I can say that on y-axis, instead of putting count or occurrences, what if I put probability density? What is probability density? Like how is the probability pegged? For example, in this area, the probability is pegged very less. So means the probable of this to happen is very less. Of or probability of you getting this value is very less. Okay. So height of people, let's say this is the case, and this is what you can call as the probability distribution curve. Okay, and it is for normal distribution. Just to mention, this is for normal distribution. Okay. Now, what if I simply try to, let's say, bring in. I hope till this point everyone is clear. So now let me bring in a image for the actual normal distribution, how it looks. Okay, please give me a second. I'm simply going to the web and getting the image. So I hope my screen is visible to everyone. So this is the normal distribution actual graph, okay, which is very much similar to what we have drawn above. If you see, okay, of course I cannot draw as good as how a system can make, but yes, this is the actual graph. Now what is these percentages? Don't worry, we'll talk about these, but this is what a actual probability density curve is. And also to mention, the area under curve is equal to 1. Why? Because it indicates the probability value, okay, it indicates the probability value. Now coming back to this, what does this mean? So what does this mean is, there are certain properties of a normal distribution. We'll talk about those now, in fact. Okay. So first thing we can see that a normal distribution, and let me zoom into 100. I'm not sure if I've zoomed into 100. Okay, it's not 100. Just give me a second. Yes, I was speaking. Okay, I was on mute. From which point did you lose me, everyone? Okay, so I was talking about the properties of a normal distribution. So that these are the properties of a normal distribution. Now, what are these? For an ideal normal distribution, these things would be present. These are derived and they are also proved. The first one is that a normal distribution is symmetric in nature. Symmetric in nature means if you look from the center, both the sides are exactly similar. Okay, like from center, if you see the if you see both the halves, both of them are symmetric. So this is what we call as a symmetric shape. It's not skewed towards any side. Okay, so this is a property of a normal distribution. Second, that the mean, median, and mode for a normal, perfectly normally distributed data would be exactly same value. Okay, this, however, is very rare, but again, for an ideal or for a perfect normal distribution, the mean, median, and mode are exactly same. Where is the mean, median, mode? It's over here. So this is the mean value. That is what I have specified. That this is the value where mean, median, mode is represented. These are the exactly same values. Okay, for a perfectly normally distributed data. Now the third point is a normal distribution follows a 68, 95, and 99 rule. Now, what is this? This says that 68% of the data, then this specifically over here, in fact, is what I'm referring to. Okay, that 68.26% of the data is within one standard deviation. Data in one standard deviation of mu minus one standard deviation to mu plus one standard deviation. This is a property. Means, what does this say? Please listen carefully. It says that this is the average. If I do average minus one standard deviation and average plus one standard deviation, that is, these are the points. 68.26% of the data will be within this particular range. Okay, 68% of the data will be over here. Okay, that is within one standard deviation from the mean. For example, let's say if you are taking the weight of a population, and let's assume that the average weight is 75. Okay, the average weight is 75 and the standard deviation is 10. Just for the assumption purposes, let's say the average weight of the population is 75 and standard deviation is 10. So means that from 75 minus 10, that is 65, to 75 plus 10, that is 85. So 68% of the population will be falling between 65 to 85 kgs. Does it make sense what I'm trying to say? This is a property. It has been proved, it has been derived that if a data is perfectly normally distributed, 68.26% of the population will fall within one standard deviation plus minus from the average. The second is that 95% of the data, 95% of the data, that is this part basically, 95% of data falls within two standard deviation, that is mu minus 2 standard deviation to mu plus 2 standard deviation. And same way, the 99 rule is that 99% of the data, 99.72, you can look for the exact number over here, will fall within mu minus 3 standard deviation to mu plus 3 standard deviation. Okay. So if a data is perfectly normally distributed, so you can say that if you move in either direction, if you say mu minus 3 standard deviation to mu plus 3 standard deviation, you'll be able to cover 99.72% of the data. Yes. Clear everyone so far? Perfect. So let's move ahead now. Now, also just want to mention one more thing. Normal distribution is also known as bell-shaped curve. Normal distribution, as I've already mentioned, is also known as Gaussian distribution. And its curve is also known as bell-shaped curve. Can you see why it's called bell-shaped curve? Because if you draw a simple circle like this, does it look like a bell now? That's why it is also known as a bell-shaped curve. Okay, let me draw that also for your reference. That is why it is known as bell-shaped curve. So if someone says that my data is following the bell-shaped curve, essentially they are referring to that their data is following a normal distribution. Okay. Now moving ahead and taking a question, and let's see how what kind of questions tend to come and how does it look. So everyone, please pay attention. Let's say the question is, what is the probability of a school bag weighing less than 3 kgs in a school when on an average the weight of a school bag is 6 kgs. So the question is, what is the probability of you finding a school bag whose weight is less than 3 kg when on an average the weight of a school bag is 6 kgs? Okay, so if we try to look into this, first of all, from the graph perspective, now usually this is how the normal distribution graph is, and we agree that okay, 6 kg is the average. Okay, so this will fall in complete center. You can think from this from the point of making uh, histograms as well, if that helps you like this. Okay, that usually this is what how it looks, if this helps you to understand. But again, we are simply calculating a probability distribution. Hence, I'm making this curve graph. Okay. So, what do you think? Where will our 3 kgs fall? So 3 kg will fall somewhere over here, correct? Which is less than the average. Another question is, what is the probability of getting a school bag whose weight is less than 3 kgs? So can I say that we are essentially looking for, let me, instead of using this lines, let me use dots. That we are looking for this area. What do you say, everyone? So can I say that this is the probability, this is the answer? What do you say, everyone? Now, how to calculate this, we'll talk about that. But visually is what I'm asking you. How to get this value, we'll talk about that. But visually, does this make sense? What do you think, everyone? So far, everyone clear till this point? Okay. So now, how do we get this probability? So we agree that okay, this is uh, the visual answer. This is the visual answer for sure. What you are saying, this is the answer. But how do? And again, I've already mentioned that area is equal to probability. Okay. Now, how to get this? Now the question comes: how to get this probability? So as I mentioned, there would be a function. So the answer is using a function. Okay. What is that function? It is probability density function for normal distribution. Now here we call it density function. Keep that in mind. We call it probability density function. Why? Called as density function for continuous probability distributions. Keep that in mind. Okay. So what is the probability density function of the normal distribution? It's a bit complex to look at, but just to simply still write it. For any value x, it is 1 by under root 2 pi sigma square e power minus x minus mu square divided by 2 sigma square. Now everyone knows what pi is, but I'll talk about the others. So sigma is simply the standard deviation. E is the Euler's number. Mu is the mean. And x is basically the value for which you are calculating it. Value for probability. Okay, for which you are calculating the probability. Okay. Now, first of all, how many of you remember integration? Integration with limits and those things. If I want to calculate probability for any particular point singly, like for just this point, I would have to integrate it with limit moving to 0, correct? Why? Because it is changing with respect to the slope is changing at every point, correct? The slope is changing at every point. Okay. Hence, you do not directly use this formula, you tend to integrate this within certain values. Like if you have certain limits, that okay, what is the probability that the bag is less than 3 kgs and more than 1 kg? And you tend to provide the limits and do the integration. Okay, then you tend to provide the limits and do the integration. So this is how it is calculated. Now, because not everyone knows how to do that, as the calculation cannot be done manually, means I'm not saying it cannot be done. It is a bit inconvenient to kind of go and doing this whole calculation by yourself. Calculation needs a manual effort, and not everyone can do it. And not everyone knows calculus basically. Okay. Or in plain sense, I will call it integration because you're not doing differentiation over here. Not everyone knows integration or remembers integration. Okay. So it's not feasible. However, I've given you the formula. So if you're good with integration, you can do it directly. But what if, as I mentioned, it's not the case with everyone? So what to do in this case? So in this case, we have a table. We get the probabilities using a table, like how we were doing it binomial. Do you remember we looked at a table in the binomial distribution? It happened in today's class itself, in fact. Okay, so we get the probability using a table. But there is a problem. There is a problem that we cannot have a table. What is the problem? The problem is the data can occur in any scale. So how can we have one table? Okay. So how can we have one table that represents all these things? Now your question would be that, okay, what do you mean by scale, Rahul? We did not get this point. You mentioned that, okay, you gave a question that what is the probability that a school bag is less than 3 kgs when on an average it is 6 kg. Then you told us the PDF formula as well. So this is the PDF formula for normal distribution. and then you told that okay, it needs to be calculated using calculus and those things. But again, not everyone remembers the integration or how to do the calculus part. So we can look at a table. It was good, but now you are saying that there is a problem. What is the problem? That how can we have a single table that is able to represent all the possible values? Means just try to think about it. Currently, we are talking in terms of ones, like bag is 6 kg. What is the probability of getting 3 kgs? What if the question revolves around the mass of planets? Mass of planets. So in that case, the weights would be or the numbers would be in trillions or much more than that, correct? Like 10 trillion, 8 trillion. What is the probability of getting a planet whose weight is, let's say, 8 trillion kgs? So are these numbers on the same scale? This one is very, very big, very, very big, and this one is very small. Are you getting what I'm trying to say? So how can I have a table that works with all the possible values? Now it could be that you are looking for the weights of particles or atoms. So this element weight is, let's say, something minus 36. This element weight is something minus 36 or minus 34. And now you're saying, okay, what is the probability of getting the weight of this to be minus 30? So now the scale is, or now the values are very, very, very small. Are you getting what I'm trying to say? See, it could be that your question might have any value scale. Does it make sense what I'm trying to say? So how can I have a single table that is able to represent all the possible values? Is it possible? What do you say? Is the problem clear to everyone? What is the problem that we have? Please give a thumbs up if yes. If no, please say no. What about others? Has no one got it? Or everyone is currently inactive? So what you're saying is that it's not possible for everyone to use the formula because it requires calculus, and not everyone remembers it or everyone knows how to do the calculus calculations. So the way around is that we can use a table. But for even a table, using a table, we have a problem. What is the problem? That we want to first of all have a table that everyone can use that fits for all the problem statements, which for all the data that follow the normal distribution. But the problem is that I could be currently working on a problem statement like school bag, which where values are simply 3 kg, 6 kg, 4 kg, 5 kg, 10 kg. And you could be working on a question which is working on the mass of planets, where the values would be 10 trillion or 10 petabillion, something like this, or 10 trillion kgs or 10 or 2 trillion kgs. The values are very, very different, correct? And someone could be working on the mass of particles, where the values are like 1.6 into 10 power minus 36, 1.2 into 10 power minus 36. So the ranges that can occur could be very, very significantly different, and there are so many ranges that can come up. Correct. For example, if you are looking at the height in centimeters, it could be 150, 160, 170, 180, 190. It can be any number because because data and numbers can occur in any shape. Like it depends what you are calculating. So what I was saying is, I'm saying that how can we have a single table if the data can occur in any value like scale. It can be very small, it can be very big, it can be any number. So, do you understand the problem then? I want to look at a table and simply get the probabilities, but I cannot do it. Why? Because if you think about this problem, how can you make a table that is able to encapsulate all the possible values? The answer is you cannot, correct? So what do we do? What do you think? What would we do? We tend to convert the data. We convert or standardize the data. Every data with respect to the table. Okay, we standardize every data with respect to the table. Means that doesn't matter if your values are in trillions, doesn't matter if someone values are 10 power minus 36, doesn't matter if my values are 3, 6, 8, 9. When we are converting, all of them come on a same scale of -3 to +3 mostly. Okay, so we do that in fact. Okay, that is what we are saying. And in this scaling, what we do, we center the data. We center the data where mu is 0. Like center the data means mu is equal to 0. When you are centering the data, the mu is 0, and the sigma is 1. Standard deviation is 1. How do you do that? Using this formula. And we call this, okay, I'll talk about using the formula like x transform or x standardized, whatever you want to call it, is equal to x original minus the mu of data divided by the standard deviation of data. Okay. Please give me a few seconds, everyone, once. So what do? We simply standardize every data Okay, with respect to how it is present in the table. How do we standardize it? By using this particular formula. Okay, now what does this formula indicate? For example, let's say if you're having a data, let's say you're having weights. Okay, 3, 6, 2, or whatever you want to say. Okay, 3, 6, 8, 2, 4, 9, something like this. You're having various entries, and let's say the average of this is just for the sake of assumption is 2, and the standard deviation is 1. So how you'll be transforming it is, you'll say 3 minus mu, which is basically 2, divided by standard deviation, which is basically 1. Okay, so this is how the transformed values will be calculated for the whole data. Getting it, everyone? Now we also call these transformed values as z-scores. We call them as z-scores. So I can say that what we do if we have a data and we want to use the table for getting the probability, what do? We simply convert the whole data to z-scores. How? Using this formula, where we say x original minus the average divided by the standard deviation. Okay, that is what we do. For example, this is how the whole calculation will look like. So far clear to everyone? And now, once the data is converted to standard distribution, once once the data is converted to z-scores, okay, before talking ahead, can you let me know what do you think? If my data is perfectly normally distributed, what would be the range of z scores? What do you think, everyone? If my data is perfectly normally distributed, what would be the range of z scores? Like, what could be the range of z scores? The transformed values, what would be their range? What do you think, everyone? The range would be 0, 0 to 1. Try to look at what you have studied so far. If I am converting a data which follows a normal distribution to z scores, what do you think would be the range? It will be -3 to +3 for 99.72% of the data. So 99.73 data will be converted to -3 to +3. Okay. Why so? Because if the data is following normal distribution, we know that 99.73 data or 72 data is within what? Is within 3 standard deviations. Okay. And that is what happens over here as well. Now my question to you is, do you agree that the average value using this formula will be converted to 0? What do you think? Have a look at it. Have a look at the formula closely. Will the average value be converted to 0? What do you think, everyone? Because see, it's x minus mu divided by standard deviation. When x is the average itself, so mu minus mu divided by standard deviation, so 0 divided by standard deviation will be always 0. Does it make sense? So the average by default becomes 0 with respect to this. And as you're dividing by the standard deviation, so it will be with respect to one standard deviation. Okay, because you're kind of normalizing it with respect to standard deviation. Hence, I can say, because that 99.72% data is within 3 standard deviations from mean, correct? So I can say, what I can say that the data range will be -3 to +3. Okay. We'll talk on this further in the next class. Let's stop over here because I see most of. So what I'll do is share these notes and we'll continue from here only. In fact, in next class. Don't worry. But I hope till this point everyone is clear. Okay, perfect. Now, if you have any questions, please put in your questions. If you don't have any questions, please request you to please provide feedback. If you like the class, please rate it 5. Only 5 is termed as good. If you did not like, please rate it less than 5. That is not termed as not good. So, and then you can drop from the class. You're also free to provide in your comments as well. Okay. So, thank you everyone. Those who are dropping. Sure to be, I'll do that. Ankit, I think we have the session next Saturday. However, if there is any change, you'll be receiving an email for sure. Thank you, Ankit. Thank you, Pavitra. Thank you, Abhay. Thank you, Toby. Thank you, Bharat. Thank you, Vasu. Thank you, Jaya, Aprajita. Thank you, everyone. Thank you, Lakshmi. Thank you, Manoj. Thank you, Chef. Okay, I do not see any questions coming up. So thank you, everyone. I am also leaving the session. See you next week. Thank you, guys. Bye.